This screencast is on kinetics and specifically how to find the rate law from experimental data. A typical problem asking you to find the rate law would give you the data, and they would tell you to find, they'd say use the initial rates to determine the rate law for this reaction. What you need to do is, this one is a simple form. I have one later on that would have more than one reactant, but this has one reactant. So what you need to do is you need to take the second rate over the first rate will equal the concentration of the second substance over the concentration of the first substance raised to a power of m. Okay? Sometimes this is going to net you an easy math and you'll be able to do it in your head. Other times you're going to need a calculator. So let's see what one looks like. So for instance, let's take the value for the second piece of data and compare it to the value for the first piece of data. It's your choice. You should be able to compare any two pieces of this data and get the same answer. Okay, and you can go back and check me later if you'd like. So if we take the rate of the second, so we're going to take 0.34 over 0.085 equals the concentration at 2, which is 0.2 over 0.1, and we're going to raise that whole thing to a power of m. We are solving for m. M is the rate order and the exponent. So when you simplify this, 0.34 divided by 0.085 should get you about 4, and 0.2 over 0.1 should get you 2 raised to the m. So you can look at this and go, well, 2 raised to the what power is going to get me 4, and hopefully you can do that in your head and recognize that the order is 2. You also can sometimes not have numbers that are nice and easy like this. What one does is you take the log, the log log of the resulting rate divided by the log log of the concentrations, and that value will equal m. And in this case, it also equals 2. What this means to your answer is that your rate is going to equal K times your CH3 COH. Wow, sorry, let me beep back up here. One more. There we go. CH3 CHO, the whole thing raised to the second power. The second part of this problem would then ask you to go on and solve for K. So once you know what the rate law is, you can plug in some of your experimental data and you can then solve for the constant. So we now know that the overall order is second order. So we can take a rate value, any of the values on this chart. I'm just going to take the first one. And we can plug in our rate, and we can plug in our concentration, and solve for K. So K would end up equaling 8.5. Now we then have to go on and solve for the units. We know that our rate is, we could assume that it's molarity per second, and we could then solve for our concentration. Units. So we're going to take and simplify, and we get K equals S to the negative 1, M to the negative 1. Here is a second example of solving for the rate law, but this one has 2 substances. So when you're doing this type of problem, you have to solve for the order for our substance A, and then we have to solve for the substance B, and it would involve 2 steps. The thing that's different here is that when the rate changes, we need to know the rate change attributed to A and then the rate change attributed to B. So you have to be careful when you pick which experiments you want to compare. In order to look at just the rate change due to substance A, we have to hold the substance B constant. So if we want to figure out A, we're going to do that in blue. We will look when substance B is constant. So substance B is constant here in experiments 1 and 2. That means that all the rate change is due to our change in A. We would then take and we would say, all right, 1 over 0.5 raised to the m power, because that's my concentration, is equal to 0.008 over 0.002. And when I solve that, I get 2m equals 4. That's a very poor 4, and I'm sorry. So we know that 2 raised to the anything power equaling 4 would get me an order of 2, second order. So A is second order. We'll go ahead and write that here. When we then go on to solve for B, I'm going to do that in red. When we look at solving for B, we have to have A held constant. So we can compare experiments 2 and 3. So to find B, we're going to take 1 over 0.5, the whole thing raised to a letter. I'm going to choose N. And then it is going to be 0.008 over 0.008. And you may be looking at that and going, okay, 2 raised to the n power equals 1. So we know that our n value in this case is 0 order. So term B has a power of 0. So our rate law would be rate equals K, A raised to the second order, and B raised to the 0 order. So you can simplify this and no longer write the B. This could then become rate equals K A to the second order. And if you went on and continued to solve for K's units, we have the rate, they tell us up here that it's molarity per minute, so we're going to go M over Mn equals K molarity squared. So my K units are going to be 1 over seconds, I'm sorry, not seconds, minutes, we're using minutes this time, 1 over minute, and 1 over molarity, also written as minutes to -1, molarity -1. So the whole process itself is not challenging, but you will need to break it down into separate steps. Keep in mind, in order to solve for the order of any substance, if there are additional substances, they have to be held constant. And you will easily be able to work through and determine the exponent. Typically, if you solve these and you do not get an exponent that's a whole number, that should be an indicator that you should go back and relook at your problem in your math.